Let's look at the overall heat transfer coefficients for flow across the cylinder. Flow across cylinder. So remember, we have the cylinder, flow is just getting in, gonna have some boundary layers, some separations is gonna happen. And there are correlations, empirical correlations that exist for that one. One of the correlations is based on the average Nusselt number for this length of the cylinder that we have is H average D divided by K is in terms of C, Reynolds number based on the diameter to the power of M, Prandtl to the power of 1/3. And that's what we refer as a Hilbert equation. We find C and M from experiments, and they have been table based on the Reynolds number, based on the values of Reynolds number that we have. Reynolds number Cm. Let's say if you're in the range of 0.4 to 4, C is 9.89 and M is 0.33. Similar for 4 to 4D, 911, 0.385. And there is a table that reports all numbers for the C and M based on the Reynolds number that we have. Reynolds number is defined rho Vd divided by mu, and V is the velocity at free stream condition. And for free stream condition, it means it's far from the cylinder, that the effect of cylinder has not been felt. So we don't get really close to the cylinder and pick that velocity, but it's going to be far from the cylinders. Now, properties for this equation, all fluid properties are evaluated at film temperature, TF, which is surface temperature of the cylinder plus upstream fluid temperature divided by 2. So there are other correlations. So this is one of the correlations, Hilbert equation. There are other correlations that you can find in the text. One of them, for example, is Nusselt number D is CE Reynolds number D to the power of M, Prandtl to the power of N, Prandtl divided by Prandtl S divided to the power of 1/4. And for these correlations, it is valid for Prandtl less than 500, greater than 0.7, and Reynolds number less than 2 power 6, greater than 1. And this equation, PRS, is evaluated at TS and other parameters, other properties at T infinity. So we do not use really the film temperature. Now, value of N, if the Prandtl is less than 10, then N is 0.7, Prandtl is greater than 10, then n is 0.37 and 36. 3736. So this is one correlation. There is another correlation. This one is I don't recall the name for that one, but there is another correlation, and that's Churchill Bernstein equation, and that's valid for a wide range of Reynolds number and Prandtl number. And the way it's defined is the average Nusselt number is 0.3 plus 0.62 Reynolds number d to the power of half. You would see these equations in your text, so in case I'm misprinting anything, 1 plus 0.4 divided by Prandtl, the power of 2/3, everything to the power of 1/4, 228000. This one is to the power of 5/8. Everything is 4 to the power of 5. And all properties are at film temperature, or TF. So these are a few correlations for finding the flow across a cylinder. They give us a value for H within about 20 to 25% accuracy. So these are empirical, and conditions could change. Another part is if we have a non-circular cylinder. So let's look at the forced convection over a non-circular cylinders. So the cross section of the cylinder, if it's not circle, let's say it's in the form of a square, something like that, or like this one, or it could be in the form of hexagon, and one of the shapes could be like this. Let's say this is D. So we get the largest side across the flow as the D, or it could be in terms of a thin plate, normal to flow. So let's say we have such a thin plate here with D. So the Nusselt number, the average Nusselt number of D, based on that one, is going to be C or e to power of m, Prandtl number to the power of 1/3. And here, similarly, C and m depend on the shape and Reynolds number, RED. And we can find them from the table in the text. Similar to the cylinder, we can have forced convection over spheres. And one correlation is Nusselt number D is 2 plus 0.4 Reynolds number of D to the power of 1/4 plus 0.06 Reynolds number of D to the power of 2/3, and Prandtl to the power of 0.4, and viscosity to the power of 1/4. Now, all properties are at T infinity. Mu s is the fluid viscosity evaluated at TS conditions for this equation, which has been developed by Tucker, is valid for Prandtl less than 380, greater than 0.71, Reynolds number 7.6 times 10 to power 4 greater than 3.5, and the viscosity ratio of between 1 and 3.2. So this is the correlations for finding the heat transfer coefficients for force flow across the spheres.